Okay, guys, so what we're going to talk about today is work. Now, when we talk about work, we're talking about the physics concept of work, but I'm going to really focus just kind of on, um, there's a lot of different work type situations, but I'm going to focus on spring problems because I don't know, I have always kind of found spring problems interesting. If you think about it, there's a lot of stuff that kind of works like spring. So a guitar string being plucked works like a string. Um, Obviously springs work like springs, and springs do make up or the spring factor kind of makes up a lot of important aspects of when you're engineering parts. So if you think about cars, there's springs involved with their suspension. Even if you don't have what you would refer to as kind of your traditional concept of a spring, you have like, so if you had something, the traditional spring, but a lot of things work like springs. I mean, you have leaf springs, which a lot of old trucks and even modern trucks somehow still have, despite it being basically a wagon type concept. Like wagons had springs, had leaf springs, where they basically just have a bunch of um, metal plates that act as a spring. So springs are actually kind of an interesting topic to me. Anyway, so, um, so again, in physics, we have kind of force, first of all. Before we get to work, we're going to talk about force. And as a reminder, force is mass times acceleration, which in terms of like derivatives and integration, we can think about it as mass times the second derivative of distance, right? So if you remember, you have your s of t. This is what we refer to as distance. And so the first derivative, s prime of t, is your v of t, velocity. And um, so that means that s double prime of t is your acceleration with time t. Okay, so that's what this is here. In the metric system, we often refer to mass in kilograms, displacement in meters, and then time is in seconds. So that leads our force to be in newtons. So newtons is kilograms times meters per second squared. So a force acting of, or excuse me, a force of 1 Newton acting on a mass of 1 kilogram produces an acceleration of 1 meter per second. So that's kind of the concept behind this like method of measurement. And we also have them with like foot pounds or like pounds and stuff like that for the American system, but whatever. Um, when we're defining work now, so work is force times the distance. Okay, so we sometimes write that as force times d. We could write that as like force times s. It's maybe a little more similar to kind of our distance formula that refers to things as s, but whatever, you'll see them both. But if force is measured in newtons and distance is in meters, then the unit for work is going to be what we call Newton meters or joules, which is more common. If it's measured in pounds and feet, then it's foot pounds, which a foot pound is about 1.36 joules. Okay. Now the thing is that work's equation works when force is constant. But what about when we are talking about some variable force? Well, in that case, then we're going to have to switch over to integration. So the work done on in moving an object from A to B is here, f of x, the integral from a to b of f of x, where f of x here is the function of force. So if we can define our force in terms of some kind of function and then integrate it along the distance that we want to work on, then we can find the force. Okay, or excuse me, the work, excuse me. So let's talk about springs now. So Hooke's law is a basic concept for springs, but it states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x, where the force is equal to kx. K is the positive constant. It's a spring constant is what's referred to. So it depends on your spring, but depending on what your spring, um, depending on your spring, the constant here is different. And Hooke's law actually holds true as long as you don't um, like rise x to be too large. Okay, so as long as you're not stretching it too far, and again, that's all relative to the spring you're dealing with, but as long as you don't stretch it too far, then it works out just fine. So we're going to use this as our force. Now again, if you think about it, the work is equal to, so again, this is work is equal to the integral of force. So what we're going to do with this Hooke's law, our force is kx. We are going to then integrate, so our work is equal to the integral of kx dx. That's what we're going to do with our spring law. So let's take a look at our first example. 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. How much work is needed to stretch the spring from 35 to 40, and how far beyond its natural length will a force of 30 newtons keep the spring stretched? So let's start with this first problem here. How much work is needed to stretch the spring from 35 to 40? Well, in order to find that, so in order to find the work, okay, from 35 to 40 centimeters. Now, work and joules and all that is in terms of meters for distance. So we're currently in centimeters. So if you think about that, that's 0.35 meters and 0.4 meters, okay? Here, the natural length is 0.3 meters, and the length for our initial stretch here was 0.42 meters. Okay, so that's the first thing, is we need to pay attention to our units because joules are going to be in meters. If we're talking foot-pounds, we're talking about feet, obviously. All right, so we want to know what is the work to take it from 0.35 to 0.4. Now that's a stretch beyond so our natural length is 30 centimeters or 0.3 meters. So the stretch from 0.35 meters would be from 0.05. Again, that's 0.05 meters or 5 centimeters more than the natural. And we're going to stretch it from there to 40 centimeters or 10 centimeters beyond the natural length or 0.1. So we want to find this integral. But the problem is, to solve for how much work is needed for this, we need to know the spring constant. So the spring constant is constant on this spring. So we're going to use our other piece of information to find this. So that is 2 joules of work. So that is 2 joules of work is equal to the integral of k times x dx when we stretched it from its natural length of 30 centimeters, so from 0, to the length of 42 centimeters or 12 centimeters or 0.12. So the integral of kx dx from 0 to 0.12 is going to be 2. So we're going to use this because essentially we have then the ability to solve for k because there's no unknowns here other than k. Over here, we're looking for work, but we don't know k either, so that's problematic. So we first need to find k based on the information we know. So that is to say, 2 is equal to the integral of kx squared, or excuse me, kx is kx squared over 2 from 0.12 to 0. So let's go ahead and do that. Let me pull up Desmos real quick. Okay, so 0.12 squared, I guess I could have done that one. That's not that hard, over 2. All right, so we get 2 is equal to this thing. Maybe I should write it, yeah, whatever. K times 9 over 1250. Okay, minus 0. The 0 plugging in is just 0. So solving for k, we're going to divide by 9 over 1250 or multiply by 1250 over 9, which I'm going to do. 1250 over 9 times 2. And so 2 divided by, no, I said I'd do that, but I already have this, so I'm just going to divide it here. Nope, I'm not. Never mind. Fine, whatever. 2 times 1250 is 2500 over 9. I guess I could have done that one in my head too. Whatever. That's our spring constant, K. So now we're going to use this spring constant to solve all the rest of our information here. So we're going to copy this. I'm going to use this again. Again, this is what we're looking for, is to find our work. But now we're going to plug in our K. Our K is 2500 over 9. And we're going to integrate this thing. So we can take this integral. Well, I guess I'll deal with it first. So our work is going to be 2500 over 9x squared over 2 from 0.1 0.05. Okay, so that means we're going to have our W is equal to 2500 over 18 times zero point 0.1 squared minus 2500 over 18 times 0.05 squared. All right, this 18 comes from 2 and 9, just in case you didn't notice that. 2500 over 18 times 0.1 squared minus 2500 over 18 times 0.05. And we get some value, 25 over 24. So our work here is 25 over 24 joules. Actually, it's capital J. We use a capital J for joules. Anyway, so approximately, what was it? 1.04 joules is how much work it is required to stretch it from 35 to 40 centimeters. Okay. All right. How far beyond its natural length will a force of 30 newtons keep the spring stretched? Okay, now we're looking for force now. As a reminder, force is equal to let's just go back here. Force is equal to mass times acceleration. Okay, never mind. We're just going to stick with our, here. This is where I was looking for. Force is equal to k times x. So with Hooke's law, the force is our k times x, where x is the distance and k is our spring constant. So if we're looking for how far will a force of 30 newtons keep the spring stretched, then that means that, again, force is equal to k times x. We're looking for our x. Our force here is 30 newtons. 30 newtons is equal to our spring constant, which was 2,500 over 9 times our x distance. So if we're looking for x, notice there's no integral here. It's just a basic physics question at this stage. We're going to divide 30 by this 25 over 9, or multiply 30 by 9 over 2,500, and we get 27 over 250. But that's our x distance in terms of meters, but that's kind of meaningless, so let's actually find that as a decimal. So 0.108, or if you think about that, that's 10.8 centimeters past the natural length. So that is to say our natural length was 30, so it's like we can pull it to 40.8 centimeters if you think about that. All right, let's do another one. If the work required to stretch a spring 3 feet beyond its natural length is 20 foot-pounds, how much work is needed to stretch it 6 inches beyond its natural length? Okay, so now we're in foot-pounds, but the concept is still the same. The work required to stretch it 3 feet is 20 foot-pounds, so 20 foot-pounds. It's not foot per pound, it's 20 foot-pounds. LBS is equal to the integral of our kx dx, where we're looking here, we're stretching it 3 feet beyond its natural length, so from 0 to 3 we get this. So we need to solve for k first again, so that way we can actually find the integral that we're interested in, that is to say find work when the integral is 6 inches beyond its natural. So we'll deal with that in a little bit. So that means that 20 is equal to kx squared over 2 from 3 to 0. We are going to plug this 3 in, so 20 is equal to 9 halves, k, minus 0. All right, so that means that 2/9 times 20 is equal to k. So our k here would be 40 over 9. This is our spring constant. Okay, so now we're going to use the spring constant to find the work needed to stretch it 6 inches beyond its natural. So this is 40 over 9 x dx. And now we're thinking we're going to stretch it. Now the common mistake here is to say from 0 to 6, but we're not doing it 6 feet beyond its natural length. These are all in feet. 6 inches, that's going to be half a foot. So 0.5 or 1/2, whatever we want to think about. So the work then is going to be 40 over 9x squared over 2 from 0.5 to 0. Or instead of 0.5, it's 1/2. That's easier for me. Okay. Now, this is 20 over 1, like that. So the work here would be 20 over 9 times 1/2 squared, which is to say 20 over 9 times 1/4. So that's 1, that's 5. So the work done is 5 over 9. And in this case, this would be foot-pounds. Now 5 over 9 is 0.56-ish foot-pounds. Anyway, so that's that. Okay, let's take a look at another one. Okay, so if 5.4 joules of work is needed to stretch a spring from 11 centimeters to 17 centimeters, and another 9 joules is needed to stretch it from 17 centimeters to 23 centimeters, what's the natural length of the spring? Okay, now what we have here is we first need to think about this. We're looking for the length of the spring. Now, when we have a spring, let's call it L for now. This is the natural length. So it's just sprung up. It's just like this. Okay, let's put my L. Now, when we stretch it, let's say to 11 centimeters. Okay, this right here is 0. This is the length of the spring when it's just naturally sitting around. This right here is essentially the stretch that occurs. Now, when we are taking the integral for work is the integral from a to b of our kf of x, or kx, excuse me. Dx. This a to b, if we're thinking, okay, the integral from like say 0 to 2, what this means is that the spring is in its natural state. So no matter how long that spring is, this is just where it sits at. And then we're stretching it 2 meters or whatever away from its equilibrium. Or if we have like from 2 to 5, what this means is we've stretched it 2 meters from its equilibrium, and then we're stretching it another 3 to get it to 5. So that's what that means. So when we're talking, we're stretching this thing 11 centimeters and 17 centimeters. What we're doing is we need to figure out, well, what is this stretch that's occurring so that we can find this length here. Okay, so let's talk about it in terms of, first off, our 11 centimeters. 11 centimeters, notice these are centimeters. We need to be in meters, so that's just 0.11 meter. Okay, but how do we find this region if we know that this is the length of our spring and this is the overall length of the spring when we stretch it? Well, that's going to be 11 minus L, but more specifically 0.11 minus L. Okay, that will then give us this region right here, the stretch, this right here. Okay, so by that same logic, we're going to go with 0.17 minus L. So the integral, however long this spring is, clearly it has to be no more than 11 centimeters. Otherwise, we're not going to compress the spring in. So this is going to be equal to 5.4 joules, and we have kx dx. So that's one of them. The other one is going to be 9 joules, and same logic, 0.17 17 centimeters minus our length of our spring. So the other one, 0.23 minus L, and it's kx dx. Now, we're solving for L. This is what we're looking for, but we actually don't know L and we don't know K either. We don't know the spring constant, but we do know is that the spring constant is just that. It's a constant in both of these. And so they're equal to each other. It's the same spring that we're talking about. So what we need to do is we need to deal with both of these equations. So 5.4 is equal to kx squared from 0.17 minus L to 0.11 minus L. Okay, now we're going to need a calculator to do some of this stuff, and it's kind of a pain to do it on Desmos for some of this, so I'm just going to have my calculator handy for it. But we're going to plug in this thing here. Oh, I did my kx squared. I got caught up over 2. Okay, so that's our integral. We're going to plug in this thing now. We have 5.4. Now, one of the things that we can do is with constants, anytime we can pull them out or put them into this thing, it's whatever. So we're going to want to move this away just to make our lives a little bit better. I'm going to multiply both sides by this 2, and that will give us 10.8 is equal to k times 0.17 minus L squared minus k times 0.11 minus L squared. That's what this thing here is. We're going to do the same thing over here at the same time. So, well, we could do the same thing over here. Possibly, we'll do it. Might as well. I said we were going to. So 9 is equal to kx squared over 2 from 0.23 minus L to 0.17 minus L. Okay, so again, same thing, multiply the 2 over. We get 18 is equal to k times 0.23 minus L minus k times, it should have been squared, 0.17 minus L squared. Okay, so essentially, we have 2 equations, which is good because we have 2 variables. We don't really care about solving for k as their end result. We just care about solving for L. But it will still involve us needing to solve for a variable to then substitute into the other. That's the end result of this thing. That's what we're trying to do here. So I think that it will probably be easiest to solve for k. And the reason why we'd want to solve for k anyway is that one, L will be a pain to solve for because we'll probably have L to different powers. Something might cancel out, but there's at least going to be a squared on this one and this one. They might cancel out, but whatever. But the other thing is that we're trying to solve for L. So if we solve for k here in terms of L, we can then replace our k over here. So it's just in terms of L, and we can move on with our lives. Okay, so 10.8 is equal to, I'm going to factor this k out of both of these. We get, so bracket, 0.17 squared. So 0.17 squared is 0.0289 minus, so we're squaring this thing. So minus 0.17L minus 0.17L is 0.34L plus L squared. Then we have minus 0.11 squared is going to be 0.11 squared is 0.0121. 0.0121. I'm just making sure I don't make any mistakes. So I am doing it on my calculator as well. Minus 0.22L plus L squared. Okay? Into brackets. All right, so doing a little bit of cleanup work here. L squared, this minus distributes throughout. So L squared minus L squared is gone. So we're just in L. That's good. 0.0289 minus 0.0121 is going to be, so we have 10.8 is equal to k times this minus that gives us 0.0168. So those are taken care of. And we have negative 0.34 plus 0.22 is going to be minus 0.12L. All right, I guess I could have done that one in my head. All right, so we are solving for k here, so we need to divide everything by 0.0168 minus 0.12L. So that means k is equal to 10.8 over 0.0168 minus 0.12L. Okay, so this is our k. We again don't care about k actually, but because we're solving for L, we actually want to solve for k first for our substitution. It's going to save us work. So we are now going to plug this in over here, but I'm going to clean this one up as well first. So we have 18 is equal to, I'm going to factor the k out, 0.23 squared is going to be 0.0529 minus 0.46L plus L squared bracket minus 0.17 squared is 0.0289. I guess I already did that. Minus 0.34 L plus L squared. Okay, so same thing as before. L squared minus L squared cancels as this distributes. Let's take a look at 0.0529 minus 0.0289. So we end up with 18 is equal to k times 0.024, and then we have plus, okay, so this is negative 0.46 plus 0.34. That's going to be minus 0.12L. Okay, so now what we need to do is we need to plug in our k for L here. So we're going to take this, substitute it in. We get 18 is equal to 10.8 over 0.0168 minus 0.12L times 0.024 minus 0.12L over 1 kind of thing, right? Okay, so we're here. So that means we end up with 18 is equal to, so this 10.8 is being distributed into the top. So 10.8 times 0.024 is going to give us 0.2592 minus 10.8 times 0.12 is going to give us 1.296 L over 0.0168 minus 0.12 L. Okay, now, if we think about this, we have L's top and bottom. So, in order to solve that, this is rational. Move it over to the other side. So I'm going to multiply both sides by this 0.0168 minus 0.12L. So I'm multiplying both sides by that. So that means 18 is distributed into both of that. So let's see, 18 times 0.0168 is going to be 0.3024 minus 18 times 0.12L is going to be 2.16L. That's equal to 0.2592 minus 1.296L. All right, we are now at a linear equation. So I'm going to add 2.16L to both sides. And I'm going to subtract 0.2592 from both. 0.2592. Okay, so 0.3024 minus 0.2592 is going to give us 0.0432, and that's going to be equal to negative 1.296 plus 2.16 is going to give us 0.864L. Okay, divide everything by 0.864, so we end up with 0.05, exactly. 0.05 is equal to L. So if we think about that, that's in meters. So that means 5 centimeters long. That's how long our spring is. Now, if you notice, this is algebra. Like all of this stuff is algebra, and it might be complicated algebra potentially, mostly just because the decimals are ugly. If they were had been whole numbers, it would have been a lot better. So the decimals made life a little annoying. But ignoring that aspect, the algebra, the calculus isn't really anything to be concerned about. I mean, we're just integrating this basic linear function. And so this is essentially our Hooke's law when we're solving for like the length of the spring. But real world, you're usually not interested in the length of the spring's natural state because you could probably just get the spring and put it down and measure it, right? It's not like that's a really, really common situation. I mean, it might be. I don't actually deal with like engineering stuff, right? In my own job, I teach. So it's not like I'm producing things with springs. So there's maybe a time when it's important, but usually the spring's length and you're often more interested in finding the work that's necessary to stretch it for manufacturing or whatever. Anyway, so that's our work with a focus obviously on Hooke's law and springs because those are the things that I find kind of most interesting. Anyway, thanks for watching.